Section 8.7 is called Taylor polynomials. The goal for this lesson is for you to be able to model transcendental functions with polynomial functions. The idea behind this is that in certain situations, we can only use kind of algebraic functions like addition, subtraction, multiplication, division, and polynomials are simple functions that operate on those four operations. Whereas a function like this blue graph, like that you see here, which is f of x equaling e to the x, you can see there at the bottom, that would be considered a transcendental function. It transcends the basic four operations of addition, subtraction, multiplication, and division. So the goal for this lesson is for us to take transcendental functions and basically find a polynomial that acts like it's that transcendental function. So I have this fun little applet here. And so I want to show you kind of what it looks like graphically to find what's called a Taylor polynomial centered at zero, or a Taylor polynomial centered at zero is also called a Maclaurin polynomial. So I hope it makes sense. We like things to be centered at zero whenever possible. So the blue graph is y equals e to the x. And then right now you can see a red line. It's horizontal. And the only thing that it has in common with e to the x is at zero, they share the same y coordinate. And so let's say I decided that I was going to use this red or orangey line. I'll call it red for simplicity. So let's say I want to use this red line to approximate values of e to the x. Well, you'd say that's a horrible idea because it really only agrees at zero. And then, when you get away from zero, your red line is absolutely not the same as this e to the x graph. And so I could say, okay, you're right. Well, let's make up a polynomial that has more in common with e to the x. Because right now the red line only has the y coordinate at zero. So let's say we want to have an equation that has the y coordinate in common with e to the x, just like this one, but we also want to make sure that it shares the first derivative. Well, you'd say, well, that's easy. That's just an equation of a tangent line at zero. And I'm sure you could handle that probably in your sleep at this point. So what you're looking at now, the new red line here, this would be a first degree Maclaurin polynomial for e to the x. It's really just an equation of a tangent line where the point of tangency is where x equals zero. So that's old hat for you. So I'm going to go back. The horizontal line would be considered a Taylor polynomial for e to the x of degree zero, centered at zero. Since it's centered at zero, it could also be called a Maclaurin polynomial for e to the x, centered. And you wouldn't have to say centered at zero, I guess. Or no, yes, you would have to say centered at zero. Sorry, wrong thing. Okay. All right, and then the new red line, that is a Maclaurin polynomial of degree one, or a first degree Maclaurin polynomial for e to the x centered at x equals zero. Now, so let's go back. So here's your first degree. Now notice that the line graph that we have here, this first degree guy, he's a better approximation for e to the x, at least like the neighborhood at which this is a good approximation is growing. Like the last one, it was only good right at zero. But this one, it kind of looks like I could use the line graph maybe from like, what did that be? It would be a pretty decent approximation of e to the x from what? Negative 0.3, maybe 0.2 to positive 0.2 or something like that. So the neighborhood around zero for which my line graph is an good approximation for the e to the x graph is kind of growing. So, but it's still pretty bad, right? So what could we do? Well, we could try to come up with a second degree Taylor polynomial. Now let's talk about everything a second degree should have. It should have everything the 0 degree and the first degree had. It should have the same y coordinate as 0. It should have the same first derivative at 0. And it should have the same second derivative at 0, or concavity at 0. So here you can see this red parabola. That would be considered a second degree Maclaurin polynomial for e to the x. So, and you can see now it's hugging the e to the x curve a little tighter. And so now I've got a bigger neighborhood around 0 for which the polynomial is acting very, very similar to the e to the x graph. But it still kind of stinks as far as like plugging in something like even like 1 or -1. You can still see a big amount of error between the two graphs. So, all right, so what if we get greedy and now we want a new polynomial and we want it to have everything in common with e to the x that this one has? Y coordinate at 0, first derivative at 0, second derivative at 0, but now we also want it to have the third derivative in common at 0 as well. And I want you to notice that this would be a third degree polynomial approximation for e to the x. And it is hugging e to the x pretty darn tight. It looks like they're really, really similar to like negative, what would that be? Negative 0.6 maybe, before you start seeing any like visual kind of gap in between the curves, maybe even, yeah, negative 0.6. And then on the right side, that, you get quite a bit more, more mileage, I suppose, because just the way e to the x is shaped, it's shaped a lot like an x cubed graph on that right side with that fast growth. So you get all the way out to, I'd say you're already all the way out to 1. So what I'm going to do now is kind of just increase the n value in this. For this applet, the n value means the degree of your polynomial that you would be getting. So if I bump it to 4, then we'd have a polynomial that has y coordinate, first derivative, second derivative, third derivative, and fourth derivative in common with e to the x. And you can see, whoops. So as I increase the n value, you can kind of see I'm getting more and more derivatives in common with e to the x. And this applet only goes up to 9, but I hope it makes sense, that this, as you increase terms on your polynomial, your polynomial graph starts kind of basically thinking it's an e to the x graph. And so, and the more terms we add or the more derivatives they have in common, the better your polynomial would be as an approximation for e to the x. So with that said, what we're going to do is back up. And for the first example, I'm going to have you kind of think this through in stages. This gets easy. It's hard at first, and then it gets easy. So what I'm going to do in the next example is ask you to find the equation of this this 0 degree Maclaurin polynomial for e to the x. And then I'll ask you to find the equation for that first degree. So those two should be relatively easy because this one is just equation of a tangent line. And then probably the second degree one is the one that's going to make you think the hardest, and that's okay. And if you're partially right and not all right, that's okay too. We can totally work with all that. You can think through the third degree, fourth degree, etc. Don't be afraid to, to be partially right. And not have it totally right. Don't even worry about that. Just get what you can out of it, and then we'll go from there. All right, so let's take a look at example 1. If you probably didn't catch the title before in the previous part of this video, so go ahead and label that section 8.7 is called Taylor polynomials. As I mentioned before, the goal for this lesson is to model transcendental functions with what's called Taylor polynomials. And what I've done for example 1 is broken down what you saw in the previous video into stages, and then I'll use this to introduce the notation. So one thing that I'm afraid I may have jumbled in the previous part of this video is the difference between a Maclaurin series and Taylor series. So we're going to start off working with basically what's called a Maclaurin series. So if you see Maclaurin series, that means that we're automatically centering it at x equals 0. And it's just vocabulary that you will get used to. And then if you see something called a Taylor series, you would have to be told what it's centered at. So a Taylor series could be centered at any x value. And I hope it makes sense. We prefer things to be centered at 0, but I do want to make sure you're comfortable. So if we can, we reach for a Maclaurin series. Now, you could say Maclaurin series, or you could, to say, another way to say Maclaurin series is to say a Taylor series centered at x equals 0. So basically, a Taylor series is that's why the title of the section is called Taylor series, or Taylor polynomials. Because those are kind of like, the family, and then Maclaurin series is just a special case of that large family. So hopefully that makes sense. So we'll start with everything centered at 0, and then we'll branch out after that. Okay. So for example 1, let's have you just worry about these first 3 here. The directions are going to be for you to find each Maclaurin polynomial. That means that it's automatically centered at 0 for f of x equaling e to the x. And I just took screenshots of the little stages from the previous video where we kept adding terms and adding kind of things that we wanted the polynomial to have in common with e to the x. Okay, so I'm going to butt out and let you think about it, and then we can go through it together in the next video.